Holy Spirit, let everything go very well in the name of Jesus. Let everything go very well in the name of Jesus. Don't call my neighbor, please. I beg in the name of Jesus. OJB, I'm already coming live. Sorry for the delay. Yeah. And this is my data line. Please, I think I'm going to avoid it. Let me shift it like this. No, you don't need to go out. But I don't need to go out. Shift it. Okay. And you can take it. But if you are comfortable on the table, you don't need to move out. Want to shift the camera already? No. You're in German. OJB, I'm already coming live. Sorry for the delay. Yeah. And this is my data line. Please, I think I'm going to avoid it. Let me shift it like this. No, you don't need to go out. But I don't need to go out. I'm going to go out. And you can take it. But if you are comfortable, you don't need to move out. Want to shift the camera already? No. You're in German. OJB, I'm already coming live. Sorry for the delay. Yeah. And this is my data line. Please, I think I'm going to avoid it. Let me shift it like this. No, you don't need to go out. But I don't need to go out. I'm going to go out. And you can take it. But if you are comfortable, you don't need to go out. Want to shift the camera already? No. You're in German. OJB, I'm already coming live. Sorry for the delay. Yeah. And this is my data line. Please, I think I'm going to avoid it. Let me shift it like this. No, you don't need to go out. But I don't need to go out. I'm going to go out. And you can take it. But if you are comfortable, you don't need to go out. Want to shift the camera already? No. You're in German. OJB, I'm already coming live. Sorry for the delay. Yeah. And this is my data line. Please, I think I'm going to avoid it. Let me shift it like this. No, you don't need to go out. But I don't need to. Okay. Okay, good morning, class. So, this morning I'll be talking about the use of Epanet for pipe network analysis. With our knowledge of fluid mechanics in year 3 and CV 403, so we combine that together for this CV 493 hydraulic engineering laboratory. Once again, my name is Muiz Babatunde Majid, and I want to appreciate Professor Oladipo for giving me this privilege to impart knowledge. So, on this slide 2, here is a diagram of a community pipe network. It has 3 pumps. So later in the presentation, we will work on this. The objective of this presentation is to understand why it is necessary to make a water supply simulation, and what to consider before, while, and during the simulation, and how the software works. Although without becoming an expert, you should be able to understand how the software works. So what is Epanet? Epanet is a computer program that performs extended period simulation of hydraulic and water quality behavior within pressurized pipe networks. It reproduces the behavior of a network in order to carry out tests and find solutions. It makes a mathematical representation of the relationships among its components. It runs trials on what would happen if you change any particular element in the network. There are other softwares that can actually model water pipe network, like WaterCAD, WaterGems, NetPlan. And you should understand that all these other theories that I've mentioned, they are for commercial purposes, and they will charge you for using the software. But for Epanet, is a software that is owned by Environmental Protection Agency of the United States of America. So they made it free. So it's an open source software. In fact, you have access to the program that was used to write it. Other softwares are WhatDis, PFCalc, Branch, and many others. The name of the person that wrote the Epanet program is Les Rossman. In the pipe network, actually, just like OAU pipe network, for example, most of the time there is always an existing pipe network. So in some cases, you may want to check, for example, now from OAU dam, probably 2,000 liters of water was being pumped, and when they measure the amount of water that was discharged at every other nodes, they discovered that the total was about, let's say, 1,800. So now 2,000 was pumped in and 1,800 was gotten. So the remaining 200 liters, where is it? So if you want to examine that, probably there might be leakage along the pipe, or probably there was a wrong mode of measuring the water when it was being pumped in, or some other fault along the pipe might have occurred. Or maybe there was an introduction of new nodes. Probably there is along the pipe network. Maybe someone added a new pipe so as to redistribute the water without informing the end engineer. So things like that can happen. So and in Nigeria, actually, there is a problem of data. So sometimes when new connections are being made to a pipe network, the engineer might not be notified, and it might not even be documented that there was a new modification along the pipe network. So there is need for data. Actually, there is need for reliable data, and for documentation of any changes that is made to any pipe network. There is need for that. Before starting with Epanet, let's look at the criteria for a successful project. The system is sustainable technically and instructionally over time. Number 2, it guarantees equal access for everybody. And number 3 is adaptable and can be altered. So actually, if you model a particular pipe network, you must ensure that it is adaptable, that it can be modified based on needs. For example, maybe you lay a particular pipe network along a particular path, and over time, maybe 5 years later, there was a settlement along the pipe network. So you want to also distribute water to people in the new settlement. So there will be need for adjustment and modification. So that means when you are laying the pipe, you must bear in mind that it must be adaptable over time. must be adaptable. Even not only water pipe network actually, Epanet can also be used for oil pipeline. Yeah, it can be used for oil to model oil pipe network. But when you are simulating it in Epanet, that means the difference between and you have to bear in mind the difference between water and oil. For example, petrol. So one of the differences is that apart from the combustibility, one of the differences is that the specific gravity of water is different from that of petrol. The density of water is different from that of petrol. So when you are modeling petrol as a liquid in Epanet, so you have to modify the specific gravity or the density as the case may be. So why do we build a pipe network? When there is a concentrated population and they need water, so you have to build a pipe network for that, so as to distribute water to the community. Then when there is population, when the population has social cohesion, and then when the water source can be exploited in a sustainable way. For example, when there is a nearby river, you can, instead of allowing the community to stress themselves to be fetching water from the river, you can set up the government rather can set up a water processing plant, then distribute it to the community. So before you can actually distribute to the community, that means you have to lay a pipe network. You have to first of all design it, then lay it. When shall we build a pipe network? One another reason is when there is need for clean water. It's not enough to just have water. The water must be clean. Like Prof will say, it must be portable, not portable. Apart from the fact that it must be PORT able, it must also be POT able. It must be portable. Then also one of the things that affects pipe network is the topography. So when you are laying pipe network, you also have to consider the difference in height or where you are laying pipe to. For example, on OAU campus, water, according to what I heard, water is being pumped from the OAU dam to a particular high point on campus. Then from that place, gravity will redistribute water to different um, part of the water network. So as to, and actually one of the reasons why you need to pump water to a very high position or point is to reduce the cost of pumping water to different tributaries, so that you will not be spending too much money, pumping water to other part of the network. Once you pump water to a very high point, from there gravity can push the water to different locations. So why should we calculate the amount of water that is flowing through a particular pipe network? Networks that aren't designed properly devalue the network and effort of communities that are asked to collaborate. And then over time, the pipe network can actually degenerate, and that will be dangerous to the health of the people in the community. So there might be need for a redesign or to modify. Then there are some kind of pipe that are very fragile, that cannot resist pressure. Probably there's a new development and they are excavating. So during the process of excavation, a pipe network might a particular pipe might actually burst. So that will affect the movement of water along the whole channel, probably. Then the network might not be extendable. That might be a challenge. And we have different type of pipes. We have concrete pipe, we have PVC pipes. So when we are um, when we are constructing a pipe, a pipe network, we must be aware of the kind of material that we want to use. We must take care of that particular aspect. Probably we want to use concrete pipe or PVC pipe. For example, on campus before, I used to see the concrete pipe before, but currently I'm seeing PVC pipes. So I think there's a change, there's a new development. So when you are constructing a pipe network, you have to be very very sure of the material you want to use to construct it, because the kind of material that you use to construct the pipe will actually affect the flow rate in the pipe. It will affect the head losses also, as we will see later in the lecture. So before we start using the Epanet software, we need to download the software and the software is very very easy to download. As I said earlier that it is open source. So the programmer Les Roseman is also an environmental engineer. He made it for he made it free for the US government. He made it free for the US government. So it's very easy to download it. So join me by opening the slide. I'm in slide 11 now. So download the software through the link that is provided there. So once you get to EPA website, actually I want to demonstrate it from this my side. I want to demonstrate it. Let me copy the link. And let me also bear this at the back of your mind. Epanet is very very easy to use. Unlike other softwares, it's very easy to use. That's why most people even use it for research purposes. It's very easy to use and it is open source. In fact, the download time doesn't really the download time is not very very long, and even when you are installing it doesn't take much time. So software, come to self-extracting installation program for Epanet 2.2. So this is the latest one, version 2.2, and it has 3.5 megabytes. You see, actually I've downloaded it and I've installed it already on my PC. So if you've not downloaded it, so try and download it and install it also. And let me wait a little bit. It doesn't take long to actually install. Once you have it on your PC, just click install, then answer yes to all the other questions and open the software. So now I'm opening the software from this particular site. I'm opening the software from my site here. So this is the first interface you see for the software. This is the first interface. So let's get familiar with the buttons and all the objects that are in Epanet. Let's get familiar with it. And it doesn't have too much functionality also. Epanet does not have too much functionality. It's very very easy to understand. And along the line, probably you want to know more about the software. So you can download the user manual also. You can download the user manual. And for the software, apart from the first example that you will see in the software, they added about 4 other examples for different purposes, as we'll see during this presentation. So what can Epanet do? It can help in determining what pipes with which diameter should be used. So you can, when you are trying to model a particular pipe network, and you want to be certain about the diameters of pipe to use at different junctions, at different points. So you can first model it in Epanet. So when you have modeled it and you run the analysis, so you'll be able to select the pipe diameter to use and the likes. It also helps to determine and also make improvements on network needs. Then it also helps to determine where to install tanks, valves, and pumps. Then it helps in dimensioning of your tank. Probably you want to know the appropriate size of tank to use. Then it also helps in pump selection. In CB403, there's a particular part there that we taught pump curve, pump selection. So it actually helps in pump selection. So during this tutorial, we'll put input parameters for some pumps, as we'll see in this lecture. Studying chlorine's behavior and necessity to establish secondary chlorination points. In water treatment plants, they used to use chlorine for water treatment. So you want to know the right amount of chlorine to use in your pipe network. In such a way that it's not going to affect the pipe, and then it's not going to affect the health of people that are going to drink the water also. So you can use Epanet to model chlorine quantity in a pipe network. Then estimation of energy consumption for pumps. For all of when I think during my own set, we went to OAU water treatment plant and we were shown pumps. If I can remember precisely, I saw about 3 pumps there that day, and they said that only two are functioning as at that time. So during this lecture, we are going to, there's a particular pipe network here that has three pumps. So we are going to model the pump and see how the pump of is in Epanet. Then when you want to measure the energy consumption of your pump, you know, even when you water pipe network itself is also powered by electricity. So once you are developing the pipe network, you have to bear in mind how you are going to power it. Probably you want to use solar energy or generator, whatever means. You have to bear in mind the energy consumption. So after modeling the pipe network, Epanet is going to give, if you give Epanet details about the energy requirement, Epanet will give you the energy consumption per day, per month, even for a year. It will calculate it for you. Simulation of the behavior of different elements, such as pressure reducing valves, pressure sustaining valves, and the likes. So Epanet will help you to observe the behavior of the kind of valve to use in your pipe network. So what is it that Epanet cannot do? Since morning I have been mentioning what Epanet can do. Now, what is it that Epanet cannot do? Epanet assumes the quasi-equilibrium condition. That is, it cannot simulate abrupt changes in the network. So it cannot simulate energy failure at pump station. It cannot simulate water hammer. And it cannot simulate sudden shutting of a non-returning valve. It cannot also simulate pipe bursting. And it cannot simulate what do they call this thing? Is it gas? No. Something just happened recently in Rivers State that they said the pipe network busted. So it cannot simulate pipe burst also, or vandalism. Evaluate the consequences for the presence of air inside the network. So Epanet cannot actually model the presence of air inside the network. And then another limitation of Epanet is that it cannot simulate open channel flow. Open channel flow. Epanet cannot simulate open channel flow. So essential parameters of a network. So during modeling, we'll be seeing terms like elevation. We all know what elevation is. Then we'll see terms like pressure. We'll see terms like velocity, then water demand, water availability, and component of the network. And some of the major components of a particular pipe network in Epanet is pipe, pump, reservoir, and valves and tanks. Essential principles for a water network. So equation of continuity. In CV 403, so we were taught, and I believe you have been taught also, equation of continuity, that is, what goes in should come out. So if you have V1, A1, let me write the equation. Okay, big diameter and low velocity. When it's coming out, it will have small diameter and high velocity. So I think we are familiar with this. We talk about nozzle. You know the concept of nozzle and diffuser. So that's where we have a equation of continuity. So this particular part is extracted from CV 403 class notes. The algebraic sum of the flow rate in pipes meeting at a junction together with any external flows is 0. And this is the expression for that. Then another concept is the friction loss along the pipe. During CV 403, I think I can remember we were taught how to derive some of these equations. If not 403, probably how to derive that's Weisbach and Williams. So if you can, in your free time, you can try and derive it so as not to forget the formula. Although in Epanet, you don't need to be cramming formula. It's already embedded in the software. You don't need to cram it. So this is Williams and this is Chesimani. So Darcy Weisbach is the most theoretically correct. It applies over all flow regimes and to all liquids. So we can use Darcy Weisbach to model liquid flow in pipe network. We can use model oil flow and the likes. Williams formula is the most commonly used head loss formula in the United States. It cannot be used for liquids other than water and was originally developed for turbulent flow only. So that means for turbulent flow, we talk about Reynolds number that is higher than, is it not 6,000 or 4,000? So Chesimani formula is the more commonly used for open channel flow. When we talk about trapezoidal channel, circular channel, and the likes. Essential principles of a water network. Friction loss along pipes. So when you talk about friction loss along pipe, that means there might be a kind of scratch along the pipe network because of, depending on the material that is used to make the pipe. For example, a pipe that is made of cast iron. So the Williams roughness coefficient is between 130 to 140. For concrete pipe or concrete line pipe, the roughness parameter is between 120 and 140 and the like. We also see that of Darcy Weisbach for cast iron 0. Then Manny's coefficient 0.0122 to 0.015 and on it goes. And you have to bear in mind that the roughness coefficient of a particular pipe network made with, say, plastic. So let's take for example this plastic now. The Manny coefficient is between 0.011. I'm talking about plastic here. The Manny coefficient is between 0.011 to 0.015. So that is the Manny coefficient for a plastic pipe. Now, in your mind, can you think of what would happen if the pipe was laid, a plastic pipe was laid in, say, year 1950, and we are in 2024 now? Can you think of what will have happened to the pipe over the years? So, I think you can guess as much that the pipe roughness will have increased. So it cannot be 0.011 again. A pipe that was laid in 1950 and this is 2024. If the pipe is still in service, I can say certainly that pipe will not be having a Manny coefficient of 0.011 again. It cannot. It will have changed. It will have changed. The same thing with steel. Steel is even the poorest. 0.015 to 0.017. If the Manny coefficient is 0.015 before in 1950 for a steel pipe, you know that the roughness will have increased in 2024 and it will have gathered a lot of dirty particles along the pipeline. So it will not be the same way again after some years. So the reason I'm emphasizing on the age of a particular pipe is because there's a particular material that is added to the slide. So we are going to look at the material together. The pipes in that material have a particular age range. So we are going to use the age range to estimate the roughness coefficient for each of the pipes. Then we also, in Epanet, we can't do without this Bernoulli equation. So it's expressed in this particular form as half rho v squared plus rho g8 plus p is equal to constant. I think we are familiar with this from MEE class. So design of a network. So the network can actually be designed as branched or looped network. So according to some studies, it is concluded that a looped network is more reliable, and although it's more expensive, but it's reliable, because in case a particular pipe is faulty, you can divert the water along another route without the burst affecting too much part of the network. So a looped network is actually much more variable, although it's expensive. Okay. So let's go back to the software. So Epanet's 6 main objects. So here we have, can you see my mouse pointer on junction? So in Epanet, we call this circular object junction or node. Let me go back to the slide. So we call it node or junction. So reservoir, that is the water source. And in some water, as you will see in the first example, you might see in some textbook you might see a particular pipe network and they do not add the water source and they ask you to calculate it. Of course, because of your equations that you have, you can easily calculate that. But for Epanet, you have to add the water source. You have to state where water is coming into the network. You have to state that. So this is the reservoir. So most of the time, reservoir is modeled directly with a pump. And sometimes you can use gravity method to model it, such that you might not really need a pump to pump water inside the network. So by just raising the reservoir to a particular elevation, water can easily flow to the network. So we also have tank, we have pipe, pumps, and valves. So let me show you the way they are printed here in the software. So we have junction or node. So in Epanet, you will see this as junction. It's also called node. Then this is reservoir, the water source. Then tank, this symbol represents tank. And this is pipe. This symbol that looks like a referee whistle is the pump. Then this is valve. And you want to add text label to whatever your model. So this is the text option. So you want to drop tool, just like those of us that are familiar with CorelDRAW, you know that drop tool or object selection icon. So this select objects button is what you can use to drop to. Probably you pick a particular object and you want to drop it, so you just come and click on select object. So a junction is a point at a certain height where water can leave the network. This outlet is created by assigning a demand. When a negative demand is assigned, it is automatically turned into an inlet. A borehole can also be shown as a junction, where the height represents the water level inside. In junctions, demand is known and pressure is unknown. So in a junction, you have to put a demand in a particular junction. Especially the first one, you have to put a demand there. Reservoir. So as I said earlier, reservoir is a typical method of modeling the water source. Probably there is a river nearby, or so you dam the river. So where the water is being stored is the reservoir. So this is reservoir, and this is the symbol. This is the symbol for reservoir. So the main parameter of the source is edge. So for reservoir, what you just need to model a reservoir in Epanet is, once you have an idea of the elevation of the reservoir, the edge. And in Epanet, once you see edge, you know that you can easily convert edge to pressure. P is equal to rho GH. So once you know the density of the liquid that you are modeling, then you know the edge, which is the height. Then the acceleration due to gravity, you know that, so you can easily calculate pressure from edge. Tanks have a limited capacity to store water, and the water level increases or decreases as they fill or empty. So this is tank. This is the symbol for tank in Epanet. This is a typical example of a tank in real life. So tanks are considered round in Epanet. So main parameters are radius, elevation, initial level, maximum level, and minimum level. Pipe. So this is the symbol for pipe in Epanet. Pipe convey the water from one part of the system to another. Epanet assumes that pipes are always full. So furthermore, that is fully developed flow. You know, in ME we were taught fully developed flow. So Epanet assumes that any flow through it is fully developed, and there's an equation for that. Furthermore, it assumes that by using their properties, they are capable of being opened or closed. So you can actually close a pipe and you can open it either by a click of a button or by programming it. There's a particular aspect of Epanet where you can also do little programming. But for this class, we will not really delve into that. We just want to look at the basic part of it. So you want to automatically control a particular aspect of the network, you can come to controls. Then you can do simple control. Then enter the program to control a particular pipe. If you know the name of the pipe already, and then you know what you want to do with it, probably you want to close it, so just program it to close and open. It will do. Then we also have rule-based also. So these are the programming aspect of it under controls. So so you can limit the flow in different directions. So as water travels through the pipe, what part of its energy is distributed by friction. Main parameter of the pipes are end node, start node, length, diameter, and roughness of the pipe. So the roughness depends, as I said earlier, that the roughness of the pipe depends on the material that the pipe is being made of. For example, this diagram we are seeing consists of HDPE pipe. And you have to bear in mind that HDPE is a particular chemical, uh, let's say, technology, and it's different from PVC pipe. So their roughness parameter will also be different. So pumps. So this symbol here that look like a referee whistle is the symbol for pump in Epanet. And most of us in our environment will have seen this pump before. For some of us that stays off campus, they will tell us in some of our residents that the pump is fault. And when they bring the object out, it looks exactly like this object here. And most of the pumps these days are powered by solar. I think that's very, very sustainable. So it is wise to avoid them as much as possible and try to create gravity flow. So when you are modeling in Epanet, it's very good to actually avoid pump. The reason is because sometimes you might not have sufficient information or data about the pump that you want to use. So as much as possible, you might avoid them and use other methods like gravity flow system. Then main parameter, start node, end node, and pump curve. So when you are modeling pump also, you have to input the pump curve data. So we are going to do that before the end of this class. We are going to do that. Valve. So this symbol here is the valve. Pressure. So and there are different type of valve in Epanet. So there is pressure reducing valve, pressure sustaining valve, pressure breaker valve, flow control valve, throttle control valve, and general purpose valve. So try to avoid in developing context due to their high cost and difficulty in obtaining spares. So if you are modeling a particular pipe network, according to expert advice, try to avoid using valves because once it spoils, sometimes it might be difficult to find replacement. And remember that non-return valve can be incorporated in the pipe's characteristics. So actually this is a little bit more advanced for this level. So now drawing the network. No need to draw precisely if automatic length option is switched off. So in this particular software now, we are going to model pipe networks. And bear in mind that under the preferences and defaults, we are going to set that the length of each pipe should not be automatic. So once it is not automatic, it will be easier to draw the pipes. So we are going to switch off the automatic length of pipes. Keep automatic labeling of the objects. Updating label will be very time consuming, so make the labeling of the object automatic. And keep in mind that Epanet doesn't have the undo option, therefore save different trials. So actually this is a challenge to Epanet, and they will have resolved it, not because it's probably government software. That's why they've not really resolved it. You're supposed to have redo, undo, just like in Microsoft Word or Excel, that you can go back to the previous edit or repeat the last division. But Epanet cannot do that. So you have to be saving each stage. So sometimes when I'm modeling with Epanet, I have to do, after writing the name of the project, probably if a community water network, so I have to say stage 1. So when there's any new changes, so I have to be able to track the changes. When I want to save another change, I will say save as if a community water network, stage 2, stage 3, on and on like that. During the network, note all the changes in order to remember it while doing several trials. So you might also document the changes that you are making in Epanet. Probably you are adjusting the pipe diameter or roughness parameter, or you are adjusting the tank or pump parameters. So you may need to document the changes for each stage, that each changes that you are making. You you may need to document it, probably on Google Doc or on your desktop in Microsoft Word or in your notepad. So let's start drawing a simple network. So come to Epanet, and the default configuration, open Epanet, select project. So before we do this, I want us to look at open Epanet, select project, ID labels. So let's go to the defaults. So come to Epanet. Actually, before you start modeling, it's very, very important that you set the defaults. It's very important. So let's come to Epanet, come to projects, defaults. So under default, we have 3 tabs: ID labels, properties, and hydraulics. So come back to ID labels. So junctions or nodes. So you want to give each junction that you model in Epanet a particular name or a particular first name. For example, the first node, if you model it in Epanet. Now let me close this window. I want to show you what I'm trying to say. So I'm modeling a node now. Now I want it to show the name. It's not really bringing a name currently. So come to properties. Come under this property browser. Click on this pencil and book icon. Click on it. Then you see the junction ID. It's having 1. Now I want it to be in such a way that every junction that I'm modeling should have a particular unique identifier. So what I'm going to do is that I'll come back to projects, defaults. So under default, set every junction to have the first letter J, capital J. So I want to do the same thing to other objects in Epanet also. Reservoirs, I want all my reservoirs to have R as the first the prefix. So I want the first letter of the prefix to be R for my reservoirs. Then tanks, T. For pipes, P. Pumps. Now we have pipe, we have pump. So I can't use P again. So what I'm going to use here is I can use link. You can call pipe link in Epanet. So let me set this as link, pipe as link, then pump as P, valves as V. Then patterns. The patterns in Epanet, you can have different patterns in Epanet. So you can leave that for the meantime. Then curves. Normally Epanet will give you curves name as 1, 2, 3. Even patterns also 1, 2, 3. So you can just leave that for now. So okay, what you have done, you can set it as default. Save as default for all new projects. So you can save it as default. So select this button. Okay. So now view. Then you also have to set. I want to follow the slide. So we've set the ID labels. We've set the prefix already. Now default properties. So come to properties. Projects, default. We've set the ID labels already. So come to properties. So under properties, node elevation, leave it like that. Tank diameter, leave it as this default value. Then auto length, make sure it is off. Make sure auto length is off. Then the pipe length, you can still set it as default. You can set the default as 1000. Pipe diameter, sure. Now, pipe diameter in Epanet is in millimeter, automatically in millimeter. Pipe roughness coefficient 100. So you can leave all these defaults. Then flow units. So this is gallon per minute. You know, in our CV403, when we are given a particular flow exercise to solve, sometimes they might give us the quantity in liters, sometimes in meter cube. Then when they say we should find the flow rate, probably in meter cube per second or stuff like that, or liter per second. So if you are modeling Epanet, you have to set this actually. So we have gallon per minute and other units. So here we have liter per second. There's no meter cube per second here. So it's better for you to convert that meter cube per second to liter per second. It's more convenient. Or you can set it to gallons per minute. You can convert meter cube per second to gallons per minute. So any of this, and in most papers, in most research papers, they used to use either gallon per minute or liter per second. Actually, you are not limited. It's not limited to the two. You are free to use other quantities also. Now, so that is that about that. So I want to leave this as gallon per minute. Then head loss formula. You see HW. This HW means is in Williams. Is in Williams. I hope I'm not going far away from the slide. Okay. Look at roughness. So so program configuration, default hydraulics. So in this hydraulics part, so I'm already explaining this. So let me go back to Epanet. So I said HW means is in Williams, and there are other options. DW, that's the waist back, and CM and Chesimani. So most of the time, people use is Williams, and then as I've said in the slide before that, is in Williams can model any liquid. No, and that's waist back can model any liquid, while is in Williams is used for water majorly. So let's set it as is in Williams. Then specific gravity of water, we know that is 1. Relative viscosity also. The maximum trials in the class, in CB403 class, we used to do 3-4 trials. So this software now we set it to do 40 trials. So once it has reached 40 trials, it should stop. So if it is unbalanced on the first trial, set it to continue. The demand multiplier, emitter exponent. Now this emitter exponent is used to model water hydrant or fire hydrant. I will show you the picture of fire hydrant in the slide later. So emitter exponent, you can just leave it as it is. Now, so we want to develop a simple network with Epanet and run the analysis. So here we are going to develop a very simple water supply composed by source, reservoir, gravity distribution, and distribution point connected with pipes. So here we're not going to include pump because we do not have all the data. And this example one is from CB403 notes. This example here is from CB403 note. This particular value of 0.1 at the inlet and 0.1 at the outlet is supposed to be 1.0, so it was a typo. So bear that in mind. And let me expand the slide. I want to expand this picture here. Sorry for that. So determine the flow rate in each pipe of the network by using at the cross method. Neglect minor losses. If the pressure head at A is 130 meter, what is the head at D? So we want to model, so here now, we want to model the flow in this particular pipe network. We want to know what is the flow rate along pipe AC, AB, BC, CD, and BD. So we want to know the flow rates in each of them. So what we are going to do now is we'll model it in Epanet. So existing data, the data that we have is the nodes. We have the node location and elevation. We have the type and length of the pipe. We have the elevation, type, and size of reservoir. And we have average water demand at water distribution. Actually, for this pipe network, we do not have, this is a typo, we do not have the size of reservoir, but we are going to model reservoir and give it a particular value. Average water demand at water distribution points. So let's model it in Epanet. So, and before you now, I want to also I want you to pay attention to this. You know, for example, now you want to model water network for a community. So, and you want to position each of your pipe at the exact point that it will be in real life. So that means you need the map of that community. So Epanet allows you to use real life pictures, real life map. So what you just have to do is that you obtain the JPEG of that map, then convert that JPEG or PNG file of the map to bitmap. We are going to do that. I'm going to put you to that. So after you convert it to bitmap, so you can easily import that bitmap file into Epanet. Epanet does not accept JPEG file format. It does not accept any other format apart from bitmap and .emf. So for this, we have to import. So inside the backdrop, so I'm in slide 36 now. So inside the backdrop map, so first develop a map and save it as .bmp. Actually, you have to first get the map in JPEG format or PNG format. So after that, convert that JPEG format to BMP. To make it easier, if you do not have the software to, actually most of these laptops have the software to, and the software or program to convert from PNG or JPEG to bitmap. So you can do that on your laptop without going online. But if you don't know how to do it on your laptop, just go online. Go online, then type convert JPEG to bitmap. So convert that bitmap and convert that JPEG to bitmap. So once you converted it, save it in a way that you can easily recognize it on your PC and know the location where you save it. So I'm going to do that now. I've already done that for a particular. Let me delete this junction. Okay. Yes. So I've deleted that. Now, so come to view. So come to view option in Epanet. Come to backdrop. Because you are not using standard map, so you don't need to bother yourself about dimensions. So come to backdrop, then load. Click on load. Allow it to load. Then go to the location where you saved the backdrop. Backdrop is the map, the background that you want to use to model the exact shape of the network that you want to draw. So example one backdrop bitmap.bmp. So this is the backdrop that I want to use. Already, to save the time, I've already converted this backdrop from JPEG to BMP on my laptop. You can do it online and you can do it on your laptop. If you use Paint 3D, for those that are using HP, Paint 3D can do it. Paint can do it. Those are the programs that I use. And there's another one on this Dell. They can also do it. So you can do it on your PC. You can convert on your PC. So this is the backdrop. So this is just picture. This is not the network. This is just the picture from the notes. So, and you can drag and you can move this picture around by coming to this option. Select region, pan, zoom in, full extent. So I want to pan. You see? So you can carry it comfortably anywhere you want it to be. Then you can zoom it in and out. So it's large enough as it is now. So the next thing I want to do is that I want to follow the slides religiously. So let me go back to the slide. So after importing it, I've imported it. So come to slide 37. Add reservoir at the spring. So the source of the water. Now in the notes, they did not actually give us any. They did not give us any parameter for the reservoir. So, but here we are going to use a reasonable value. So, reservoir. This what I selected now is junction. I want to select reservoir. So this is reservoir. Select reservoir. Then you can see that water is coming in through this side. So reservoir should be positioned somewhere close to that. So I've already positioned my reservoir. Now immediately I'm dropping any object. I want it to be showing the name. I want the name of the object to be showing. So for that, I have to go and set it up. Come to options. So when you come to options, nodes. Let it display the border and junctions. Come to links. Let it display if you want to proportional value or display border. Come to labels. Then come to notations. Now all the notations, they are not highlighted. So I want all their notations to be showing. So come to display node ID, display node values, display link IDs, display link values. So after that, and you can increase the size of those IDs. But for now, I think the size is okay. This size, font size 7 is okay. So then come to symbols. Make sure you click all this. Then come to arrows. Now the arrows is none. The arrow will show you the direction that the water is flowing in the pipe network. And you remember that when we are calculating in CB403, if you are getting a negative value, that means the water is going in the other direction. So yeah, just click on field. or you can click on fancy, but field is okay for what you want to do. And you can increase the arrow size, say 8 or 7. Let's say 7. Then the background color, white is okay. So okay that. Now, what do you see now? You see that the reservoir, because I already said that my reservoir prefix should be having R in front of it. So R is already in front of the first reservoir, R1. So this is my reservoir. So let me go back to the slide. Then eventually zoom in. I've done that. Now join the network. Click twice on R1 and add the parameters. Setup of borehole or reservoir appears. Coordinate do not play a role here. Blah blah blah. So come to total edge and input a reasonable value there. So let's put for this now. So these are reservoir R1. So for this, I want to put. So for this total edge, let's put a reasonable value there, because in the notes we're not given, but we have to demonstrate the source of our water options. So click on the object. So once you click on the option, on the object rather, in the property browser, it should be displayed. Then click on the object edit properties, edit. You see this pencil and book icon under the reservoir. So click on it. Then here under total edge, put a reasonable value of edge. Say 20 meters or 10 meters. Okay. So okay that. So it already have 10 meters as the edge, as total edge. Now come back to the slide. So let's go to the next step. So the next step says add junctions. So add all the junctions. And in the picture we have 1, 2, 3, 4. We have about 4 junctions to add. So let's start adding them. So junctions or nodes. So come to this add junction. Click on this circular button. That is junction symbol. So come to this on this background. This is our backdrop. So this is the position of A. So you can just drop the junction at that A. So you see J1 written there. Then at this point, and you can modify the name later, but for now leave it like that. So at this junction C, you can put another junction there. B, put another junction there. Another junction. And as you are dropping the junctions, you see that on the project property browser, you will see junctions display, and then you see all the junctions that are available in the project. So after that, you have to drop the tool. Come to select object symbol, click on it. So as to drop the tool. Then you select the object, and then you click on the book icon, book and pen icon. So now look at this. The elevation of this point, the elevation, you can leave the elevation like that, but the base demand there, you see this 0.1 actually it was a typo, because later in the notes 1.0 was written there. So let's put 1, base demand 1. For the demand pattern, leave it as it is. It's not applicable in what you want to do there. So leave it as it is. So after you have modified J1, that is this junction 1. Now to make it easier for ourselves, we might rename our junctions as the backdrop. So I want to rename this as A. So you see A written there now. So I want to rename junction 2 as C, according to what we have in the backdrop. And I want to do the same thing for B, and for this J3 as B, J4 as C, as D. It's because the network is not very voluminous. So that's why I have the time to be changing the names. In a situation whereby the network is very voluminous, you might actually consider not changing the name at all. You might just set up a prefix for it from the beginning, like I have done before. So now I want to change the elevation. Okay, the elevation, leave it as 0, so that water can just flow from this 10-meter reservoir down to the network. Then base demand. The base demand here were not given, so leave it like that. Come to base demand for B, we are not given, leave it like that. Come to base demand for D. The base demand for D is 1 also, not 0.1. Later in the material, in the notes, they put 1.0 there also at the exit, so put 1.0. So leave it as it is. So we can close it. So after that, something is lacking in our pipe network. And what exactly is that thing? So for you to know what is lacking, actually you should be guessing it already. So let's go to view option, come to backdrop. You see, because you have already loaded the backdrop, so we have different options that you can load it, you can align it if it's not aligned, but our own backdrop is aligned already. And you can hide it. And I want to hide it now so that we can know what is lacking in our network. So hide it now. You see that there is no pipe connecting all the junctions together. So we want to add pipe now. So on hide it, show you the pipe, show the backdrop. So I want to add the pipes now. So come back to the slide. Now when you come back to the slide, we've add junctions, okay, then add the junction properties. So this screenshot here are exactly what I have done in the pipe network. So you can follow this, but this x coordinate, y coordinate, because you are not using a standard geographical map, doesn't matter. So it doesn't matter if it's different from what we are having there. But this elevation, try and keep it the way it is here. I will explain this later in the text. I will explain this part also later in the text. So adding the pipes. So we want to add pipe now. So the symbol for pipe is this. So let's go back to Epanet and add our pipes. So connect the reservoir to junction A. So that is connected. Then another pipe from A to C. So that is our pipe AC. Then pipe C to D. Pipe D to B. Pipe B to C. And pipe B to A. Now, there's an error in the way I'm modeling it. Escape. The direction where you are picking, where you are starting from and where you are stopping also matters in Epanet. So let me delete what I've done and remodel it. I want to assume that water is flowing from the reservoir. It flows to A distributes to C, also distributes to B. Then I want to assume that C distributes to B, and then C distributes to D, and B distributes to D again. So I want the pipe to be flowing. I want the water to be flowing this way and not backwards. So if you are drawing the pipe C to A, it might not really be very appropriate. It might not be appropriate. So let's delete it and redraw it again. Delete. Okay, so actually I remember that I drew from R1 to A. So that one is appropriate. So select the pipe symbol, draw from A to C. Actually, if there is an error in your pipe direction, you can click on the pipe and then reverse the direction. But I just want to give you the best practice. So A to B. There's an error, there is a mistake in where I clicked. I'm supposed to click on the node. So escape and redraw. So B. Then I want the water to flow from C to B. Then I want water to flow from B to C. And B to D rather. And from C to D, water should flow there also. Okay. So we've modeled all the pipe now. And I want to rename my pipe also, so that we can track the changes later. So for this L1, we do not have it in the node. But for L2, for this link 2, so let me select the pipe. For this pipe L5, because I've deleted it, so that's why it's having a different name. Doesn't matter. Because I've deleted L2, L3 up to L4. That's why it's having name from L5 down to L9. Doesn't matter. So I want to change the names. So this pipe L5, I want to name it, because it's between A and C, I want to name it as pipe AC. So come to this pen and paper property of the object. So click on it, then to display the property of that particular object that you have clicked. Then under pipe ID, change the ID to AC, because it's between pipe AC So do the same thing for the next pipe. It's between A and B. As you see, it's blinking. For you to be able to trace which pipe you are dealing with, you see the pipe blinking. So this particular one is blinking. So AB, then pipe BC, that's our L7. So I did the property BC or CB. So because I said that the water should flow from C to B, let me name it as CB. So if it is not, if the direction is not appropriate, it will tell us in the result. It will tell us. Then CD, which is L9, CD. Then so that's our CD. Now L8, that is BD. So after you've done that, you can close the object property. And since morning, I've not actually saved my work. I've not saved it. For best practice, it's better for you to save your work so that maybe you are using a desktop laptop. Maybe your laptop doesn't have a backup or one thing or the other. It's better for you to save as much as possible. Currently, Epanet does not have auto save. So save as example. Okay, sample. Let me say sample 1. Okay. Epanet. Let me say it under downloads. Save. So okay. So now it's back up already. So we have this now. So let's go back to the slides. Slide 44. So slide 45, adding the pipes, insert parameters for the pipes, add the rest of the links. So after you added that, so you have to go back to the pipe properties one by one. So these are the pipe. This, you can see this inside this slide. You see this screenshot. So this is the pipe, and then if you select pipe AC, this is the property of the pipe AC. Now under pipe AC, give it this particular property as you see it here. So for the length of the pipe, give it 1000, diameter 400, roughness 0.012, loss coefficient 0. Loss coefficient does not matter in what we are modeling currently, so you can leave it at 0. Initial status, let the pipe be opened. Don't close it, and don't put a valve there. Leave it as it is. So it can have a check valve to restrict flow. Don't close the valve. Don't use check valve. Just open the pipe. So leave it as it is. So the next slide shows what is expected of each of the pipes in the network. So let's quickly put all these properties in the pipe. So for the first pipe here, for the pipe AC, we can follow the notes, what is given in the notes, in the class notes. Let's still have the notes there. Okay, I think I still have it there. Okay, not there. But I have it in this slide. Okay. So for pipe AC 1400 0.012. So let's quickly put those parameters. 1000, then the diameter 400 in mm, roughness 0.012. Loss coefficient not appropriate to that. Then pipe AB. Check the properties of pipe AB. So from the slide, pipe AB has length 1500 and roughness of 0.012. 1500. 0.012. Then our pipe CB, okay, CB, here I said BC, so it has length 1000, okay, 100, supposed to be, is it 100 in minutes? So I have to check the note. So 100, 400, and 0.012. So I want to check the class question. So pipe BC, okay, pipe BC is having length 100, so that is very correct. Length 100. So take note of that. Pipe BC is having length 100. So our pipe BC is having length 100, 100, 0.102. So length 100, 500, 0.012. Then BD. Now BD 1500, 1500, 0.012. CD. These are pipe CD. The parameters are 1300, 0.013, 1300, 1300, 0.013. Okay. After that, what else? So pipe BC, pipe CD, uncheck property again. 400, 400, 400, 400. Okay. 400, 400. Is it the same? So it's supposed to be 400. Okay. So ensure that all the parameters are correct. Then our pipe RA. Let me name this also as RA so as to follow the slide. RA. That is from reservoir to junction A. So 1000. The diameter is 200. Let's do diameter similar to the other ones, say 400 or 500. Then the roughness, say 0.012. Note that this RA is not part of the given parameters in the notes, in the class notes or exercise. So we can close this. So after that, after inputting all these parameters, drawing the network, it's better to know the type or brand and their properties of the pipe. So you see under the roughness, you see that we're using 0.01 something, 0.01 to 0.013. So which of the equations does that follow? So that is Mani. So that is Mani. Mani in Mani's units. Okay. So after that, after inputting all the parameters, so let us run the pipe network. So if there's an error in the network, it will tell us that there's error at a particular location. It will tell us in the status report. It will tell us. So let us run the analysis. And it doesn't take time to run. Within milliseconds, you will get the result. So click on this fire button. You see this fire button here. Come back to the project Epanet program. Then click on run. If you don't want to use this button, you can come to project and then click on run analysis. It's the same result you are going to obtain. So click on run. Run was successful. Run was successful. And so to actually see this very clearly, I want to hide the backdrop. So this is our pipe network. So this is our pipe network and the program has been run already. So come to the object browser on the upper right hand corner. So click on map. So under the map you see node. So node is like telling that's where the junction properties are, node or junction. So under that, click on elevation. So it will display the elevation of each of the junctions. Then under links, and I told you initially that links also means pipe. So click on links. Then under the button under it, click on flow. You want to see the flow. Now you see. So here we have 0.36, 0.64, 0.13, 0.22, 0.78. If you compare these values with the class notes, It's just few decimal places different from each other. So let's compare it. So this slide is talking about the analysis report. So come to this now. So you see that if you compare the answer from the hand calculation and the software calculation, this is hand calculation. What we have here is the hand calculation, and what we have here is the simulation result. If you compare the answers together, you see that it's almost the same. Pipe AC has 0.363 using hand calculation. From the software, we have 0.36. Now come to pipe A B, we have 0.637, approximately 0.64. So we have 0.64A in the simulation result. Come to pipe C B, we have 0.149. Here we have 0.13. Come to pipe C D, we have 0.214. Here we have 0.22. Come to pipe D B D, in the hand calculation we have 0.786. Here we have 0.78. So you see that the result is not really far away from each other. So Epanet can, if you want to do this calculation with your hand now, it will take you about, say, 20 minutes. But with Epanet, if you know how to quickly drop the node at each location, connect the pipe together within, let's say, 8 minutes, you are done with it. So it's actually make it faster to model pipe network. Now, this is just a very simple network. So now let's model a little complex network, a community power a community water pipe network connection. Let's model that. I hope the class is still following me. Okay. So let me go back to the slide. Now, we want to develop, and for this particular pipe network that we modeled now, it's a very simple one. But imagine that you want to model for, let's say, OAU. Actually, I will have presented that of OAU because Prof has given me the one for OAU. But when I was checking to the DAG and the plots was, there are some stuff in the plot that are not very clear. So that's why I wasn't able to complete the modeling before this class. But probably if I still have more time, I can actually present on that of OAU also. But I have another network that has complete detail. So I'm going to present that here also now. So imagine that you want to model for, let's say, OAU, for example, and you want to see, you want to examine the quantity of water that all students use, let's say, per day. Then you want to know the amount that you'll be supplying to them per week, or let's say a month. And you want to know how much money school will be spending on water supply every day, in a week, in a month, or even in a year. So Epanet can actually help you to estimate that. It can help you to estimate, once you know the cost of the energy, you can estimate the cost of buying fuel and the likes. So you want to model that, and then and if you actually want to model something like that, then you will need time dependent analysis over time, say for 24 hours, for 2 days, that is 48 hours, or for 3 days, 72 hours, and the likes. So you want to model something like that, and before you can model something like that, so you have to know, okay, what is the quantity of water that they use in that particular pipe network, say in around 12 a.m. in the middle of the night. Imagine, can you compare the amount of water that people in the community use around 12 a.m. in the middle of the night compared to when they are waking up early in the morning around 5 a.m. preparing to go to work and the likes, or preparing their children for school? Can you compare the amount of water that they will be using? If you say the amount of water is 100%, and that is 1.0, so the amount of water they will be using around that 5 a.m. will be close to 100%. It will be close to 1.0. You can estimate it as say 0.85. But the one for 12 a.m. in the middle of the night, maybe someone just want to flush the toilet to urinate in the middle of the night, or just want to shower. The quantity of water will not be much for most people, for most of the people. So it will be around, let's say 0.3, 0.35, 0.4. You understand that kind of stuff. So we want to model something similar to that. So before we do that, and before we do that, for such analysis, we need to develop patterns, behavior changes over time, as I've explained. So we want to develop a community water supply composed of reservoir, density distribution also, distribution point connected with pipes. Then not only that, we want to show so in this community owned, we'll be modeling a pump that will be pumping water from water source, and then there will be much more distribution points than the first simulation. Then we model, and in this particular one we are given a lot of data. So a lot of data is available for this. A lot of data is available here. So here, let me expand this part of my slide so that everybody can see it clearly. So in this particular in this second simulation, we'll be having 72 junctions altogether. We'll be having 2 reservoirs, and then we'll be having 2 tanks. Number of pipes 108. The number of pumps, there will be 3 pumps in this. The number of valves 0. Flow units will be using liter per seconds. So that's that about that. Now, because the time that it will take to actually model about 72 junctions, add 108 pipes to it, and then connect. Of course, it's very easy to connect the pumps. Then now, after dropping the nodes and junctions, and the junctions, after connecting the pipes, you still have to enter each of the pipe characteristics one by one. You have to input just like we have done before now. You have to input the length of the pipe. You have to input let me go back to the slide that talks about that. Okay, for example, now this is the pipe now. For 108 pipes, so I have to input the length of the pipe, diameter of the pipe, the roughness coefficient of the pipe, then maybe the initial status, maybe it is open or closed, and the likes. So because of that, and then I have to ensure that the start node and end node are not contradictory. So it will take a lot of time actually. 3 hours we are still there. Yeah, I can assure you that. 3 hours we are still there. So because of that, I've already modeled the network, and I've sent the model. So you can also run it over there if you have already installed the software. The software is very easy to install. Once you download that package, just 3.5 megabytes. So just install it, then go to open. So if you have the software there, I want to ask OJB now. So excuse me. Has anyone installed the software over there? Okay. Um, can you use this drive link to open the second simulation? So open the second simulation. So I also open it from my own end here. Let me save my work. As I said, if you want to track changes, you might need to save in stages. So let me practice what I have preached. So save as, I've saved it already, but I want to save in stages so as to track my changes. So save as stage 2, sample Epanet stage 2. So I want to close the program now. So actually for me to open a new project, I don't necessarily need to close it. I don't necessarily need to close it. But to make things easier for everybody, let me close the program and open a new one. So I want to use the link. So click on community water distribution system .net. Yeah, that's .net file. This .net file, community water distribution system .net file. So click on it, then download it. Download the file. After downloading it, open it in Epanet, or just make sure you know where it is saved on your PC. Then go back to Epanet, open your Epanet. Open your Epanet, then go to files. Click on open. Once you know the location of where the file, that .net file is saved, that community water supply is saved. So locate it. Actually, it's not under this location on my own PC, so I have to navigate to the location. This PC, Windows. Okay. Let me go to home. It's under my downloads location. So I've seen it on my own PC. It's located under downloads on my own PC. The one might be located under documents. So try and search for it, or make sure you monitor where it's being saved when you are downloading it. Or you can just control it to go and download under your desktop. Anyone. Make sure you open it. So community water distribution system.net. This is the .net file. Actually, Epanet's file extension is in .net format. .net format. So open this .net extension, community water distribution system. So click on open. Now, immediately when you click on open, it will be, because I've already modeled it before, and when I did modeling, actually, we did calibration, simulation model, and we did calibration, we did validation. So for this class, actually, that might be too much for the class. So that's why it's asking me for prior calibration text file. So for now, you can just say okay. Then it will ask you for flow calibration again. For the scope of this class, you might not really need to touch that aspect. And just click OK. Then could not find backdrop. Actually, you need the backdrop here. Yeah. So try and search for the backdrop. I'm coming. Have I not deleted it? Let me check. You actually need the backdrop here. Let me check online. So don't OK the backdrop yet. It's under the file it's under that link. So here it is. I've already converted to .bitmap format. So it's saved under my downloads location. Okay. So it's under this now. What's the name? Example 1 backdrop bitmap. Example 1 back. Oh, this is not the one I want to use. The backdrop. Okay, I did not copy the backdrop. Okay, this is the backdrop for the model. I've seen it. So download it also. Try and download it, add that to your site there. Okay. So backdrop for modeling. So once you are done with that, so come back to Epanet. So it's asking you for the backdrop, and it's saying, do you want to search for it? Click on yes. So search for it on your PC. So it quickly brought me to my downloads folder. So this is it, backdrop for modeling community water distribution system. So click on it. Okay. So once you click on it, you see this raw display. So actually, I modeled the network based on that backdrop, and as I said initially that this backdrop, this background image is a real life image actually of a particular location. So you want to lay your pipe according to the way it's going to be in real life. So you need a backdrop or a map, a background map to lay the pipe on, so that when you want to bring it to actually that one will even help you to see the way to look physically. Yeah. So it's help you if you are, for example, now if you're modeling for a particular community now, you'll be able to see where the road is passing, where you will need to do a lot of excavations and the likes. So that's why you need a backdrop to model exact the representation of the network. So now for this network, I just want to show you how to import the backdrop. But for this one now, we've already imported the backdrop. But let's assume that the backdrop is not even there before, or you just want to start it. So you can unload the backdrop. It has been removed. You can go to view, backdrop, load, then come to backdrop for modeling, then click open, and then it will come back again. So but for now, you see that it is ruffled kind of. So I want my screen to be looking presentable. So I don't need the backdrop again. And the reason why the backdrop is also not aligned with the network is because this is not the way I started it. So you can actually adjust the backdrop. You can pan it, you can adjust the diagram to fit the backdrop. But for now, to save time and for what you want to learn, so we skip that aspect of fitting the backdrop with the model. Actually, you have to be fitting the model with the backdrop, not the backdrop with the model. So you have to be adjusting the model to fit with the backdrop. But for now, let's just skip that aspect of backdrop. You can do that intuitively by yourself. So hide the backdrop. So now this is our model. So if you observe this model, as I said before, we have three pumps, 1, 2, 3. And if you click on one of the pump, the object browser, this project browser here will quickly bring you to the pump data. So click on one of the pumps. You see pump 201, pump 202, and 203. Click on pen and paper icon underneath. So that property icon. So you see pump 201, the properties of the pump. Now I want you to pay attention to something. Pump curve. The pump curve is written as 1. So it actually have an implication, as we later see in the slide. So let's go back to the slide. Since we have already imported the model, let's go back to the slide. So necessary data related to the Epanet network. So this is the network, and these are the data actually. Now for this particular table is showing a symbol of, is showing a description of how the necessary data are being obtained for a particular pipe network. Say okay, for a particular settlement 2, and they have 20 families. Then what is the water demand for each of the for each individual in that particular family? So once you know the water demand for each individual, for example, now if you divide 4,000 divided by 20, so 2 here, 0, 0, then 2 here, 200. So that's about 200 liters per day for each member of the family. Okay. So if it is 200 liters per day, so that means each member of the family will be getting 200 liters per day, and the person will be using 200 liters per day. So you can now use that to model the network, and then determine the kind of pumps you are going to use, and then the size of the tank you want to use for that house or community. If it's for example now this particular data here is showing for a community, and it's showing for different settlements there. So if you know the number of families that are there, and then it's not even individuals, 20 families. This one says settlement 2, 20 families. So each family will be having access to 200 liters per day. Of course, that should be enough actually. That should be enough. Let's see. So each family, and the family consists of about, say, 3 people, 4, 5. So each family will be having 200 liters per day, and then 20 families will be having 4,000 liters per day. So if you sum all this together, it will give you the amount of water that you need in that community. So for example, now total families 170, total number of individuals 850, total amount of water that is needed 34,000. So with that now you can now design the amount, you can find the appropriate size of tank to use. Probably you don't want to use just one tank, so you can calculate for, let's say, okay, 34,000 litre per day. So what kind of tank can we bring to this community that is going to be enough and adequate to satisfy the need of the people in this community? So you can project with that. Actually, when you get to year, as we come back from IT, once you get to year 5, CV 501, Prof will actually teach you water demand, or again, you will be taught water demand again. You will be taught population projection. That was the one that I said I will show later. Where is the population projection? I jumped it in the initial part. Yeah, population projection. I said the formula somewhere. Okay. So this is it now. So population projection. So you can do the arithmetic projection, geometric projection, exponential projection for the population. For example, in that community now, let's say that there are 850 individuals in that community. So you can do arithmetic projection for the population to ascertain, okay, the next, so as to design for the next 10 years or 20 years. You know that people they will be giving birth to more people. Strangers will be coming to the community and going. And of course, naturally, some people will leave the earth. So you want to project for the population, so you can calculate, okay, what will be the growth. If you know the growth rate, you can calculate what will be the population in 20 years time. So with that now, you can design the pump and the water system to last for like 20 years, to be adequate for like 15 to 20 years. So that is the essence of population projection in water pipe design, water network design. Let's go back to the main stuff. So then you also determine the type of pipe that you want to use. So I want to do something here. The folder, this folder that I give you access to. So try and open the folder and you will see a particular assignment there. Don't look at it as if this is for MSc or blah blah blah. No, don't look at that. Just look at what is inside it. It's not too difficult. It's what you are familiar with before. So this is the, let me expand it. So this is the notes. Try and look for this notes inside the folder that I give you access to. So look at the pipe. This is where the pipe data was given. So for pipe 1, pipe with ID 1, where it will be connected, it is time consuming to track all these ones. So when I was modeling the network, it took a lot of time to do that, a lot of hours to do that, because you have to trace pipe 104, where to start from, where it will end, input the pipe length, pipe diameter, and the likes. Then you have to also determine the roughness of the pipe. For example, cast iron pipe that you have here, pipe 1 is made of cast iron, and the pipe age is 20 to 30 years. So the roughness will have changed over the years. The same thing with PVC pipe, the same thing with MDPE pipe, and the likes. So these are the pipe data. So come to table 2, network junction data. So for the network junctions also, for example, junction 1, you have to look at the elevation of the junction. You have to look at the elevation of the junction. You have to look at the baseline demand residential. You have to look at the baseline demand residential and baseline demand commercial. But for now, let's just look at the residential own. That is in a place where people are actually living. So elevation of the junction. So at that junction, the residential demand. I'm sorry. So baseline demand residential. For node 1, for this junction 1 or node 1, as I said that in Epanet, junction is also known as node. So for this node 1, 38.7 meters high, then the baseline demand at that place, at least the amount of water that must pass through that place is 5.1 liter per second. I mean, the flow rate should be 5.1 liter per second. That is actually the demand. And for the other ones also, let's look at node 31 from this given table. The elevation is 36.16. So when you are entering the data for this node 31 now, you have to put 36.16 as the elevation, and then for the baseline demand residential 3.9 liter per second. So let's go to the next page. On and on. So you see that the data that you need to input for this pipe network is actually much. The same thing with that of OAU also. I have some data about it already, and I've even started work on that. But there are some things that are missing out. So that's actually what is delaying the work. You have to input some amount of data actually. So residential demand pattern. So now, because it's a community pipe network design, so you want to model for 24 hours. So for this assignment, we were given to model for 24 hours, 1 to 24. So for example, now at 1 o'clock, 1 a.m. in the morning, 1 a.m., middle of the night. So the demand is 0.68. Probably people that want to shower before they go to bed. People don't cook at that time. Just shower. Then 0.51, 2 a.m. What are you still doing awake 2 a.m.? Maybe you just have, maybe you are having an exam to write or something. So 0.51. At 3 a.m. 0.51. But let's go to 6 a.m. in the morning, 0.68. So the water demand will come up again. And when you get to around 8 a.m. in the morning, even 7 a.m. 0.85, 8 a.m. 1.02, you see that the water demand is increasing already because people are awake and they are doing their domestic activities already. So I think the highest time that we need water in this particular time pattern. I'm using this pot. Now, here the highest, the time that we have the highest demand is by observation. I think it's around 6 p.m. in the evening, 18 o'clock, 18:00, 6 p.m. 1.36. Oh, 7 p.m. Probably people that are coming back from work, cook for the family, or people that are praying for Muslims, or yeah. So I think 1.53, that's the highest. People that are coming back from work, cook for the family and the likes. So 1.53 is the highest demand. Then for the commercial, let's look at commercial environment. You just see that from 1 a.m. to 6, because it's commercial environment, people are not really there to use water. Like the demand for water is not really high from 1 a.m. to 6 a.m. For example, in a market environment, let's say a particular market, for some of our towns and cities, they have a particular environment dedicated just for selling and buying alone. People don't stay there. So for that kind of environment now, from 1 a.m. to 6 a.m., they don't need water. But starting from 7 a.m., when they will be opening the gate of those places, people will start demanding for water. So 0.5, then from 8 a.m. up to 6 p.m., 1.0, then 7 p.m. 0.5, and then when they close by 7, there's no need for water again. From 8 p.m. to 12 a.m. in the middle of the night. So, and on like that. Now, let's look at the table 5, tank or reservoir data. So, for the reservoir in the project, we have only 2 reservoirs, reservoir 103 and 104. And then look at the elevation 14 and 10. So that means that reservoir is at an elevation of 14 meters, while that of reservoir 1.104 is at elevation of 10 meters. And those two, elevation parameter for reservoir is actually enough to model the reservoir. Then for the tank, you have to look at the elevation of the tank, where you position it, and then the initial water depth in the tank, the minimum water level in the tank, the maximum, and then the diameter of the tank also. It's important to factor that in also when you are modeling the tank. Let's look at the pump data. Yeah. Now for the pump data, you need the pump curve, and then the upstream node and the downstream node. You need the pump curve. So you can, we have 3 pumps in the network. You can model 3 different pump curve for it. But for this particular work, it's just one pump data one pump curve that was given. So that one pump curve can be used to model for the 3 pumps in the network. So this is the pump curve parameter. So at 0.0 liter per second, the head is 101. At 252, it is 92. At 504.7, it is 65.2. And like, then the efficiency of the pump, when we are being taught about pump, we used to mention pump efficiency. So the efficiency of this particular pump here is 75%. Let's go to the next data. Now, calibration and validation data. So for the scope of this work, we will not delve into this aspect because this actually deals with model. When you're talking about this concept of machine learning, yeah. So we will not delve into that here. So I want to go back to the slide now. So slide 55 now. So inside the backdrop, we've done that. Then join the network, add reservoir at the appropriate points. So we have two reservoirs, so add them at the appropriate locations. So we've done that in the network. Then slide 7, join the network. So as I said, that is a very complex one. So you have to take your time. If you actually want to do it, of course, I can guide you, but it will take a long period of time. So you have to be patient to insert all the values one by one and accurately. So add junctions. So you have to add all the junctions appropriately as seen on the table in that particular brief that I sent. Then so the junction properties. So you have to input the junction properties as seen here. Even for the pipe also, you have to input them also. The parameter for the pipes, you have to do that also. Then elevation of junctions. You consider the real height of the outlet of the pipe, not just the ground elevation. Consider putting a junction at each height and low spots. Draw the section of the pipe. Then demand. Demand can vary during the day, week, season, culture, as I mentioned initially. Demand is different depending on the type of settlement. Maybe markets, that is commercial or residential, that is where people are living. Camp, rural, semi-rural, urban, industry, agriculture. Consider water demand for cattle. Demand needs to consider the growth rate, normally over 30 years. Consider extension of the network. Design easily enlargeable network. EV plan the construction in several phases. Evaluate the plan and evaluate the construction in several phases. Then model is designed for the peak construction point. Then this peak construction point, fire extinguisher, also known as fire hydrant, that is where you can get water for emergency purpose. You can also model that inside Epanet. So actually this particular part you'll be taught more about it in CB 501, but let's still talk about it a little. Simplify table of basic survival water needs. Survival needs water intake, drinking and food. 2.5 liters to 3 liters per day. Depends on the climate and the individual physiology. Like in Dr. JJ's class, we were told that as an individual, as a normal individual, you should take at least 2 liters or 2 to 3 liters per day as a normal individual. So that was in CB 305 or so. So basic hygiene practices, then basic cooking needs, total basic water. So all these ones you can get yourself familiar with it. 2 people per tap. So you also design for the water outlets like tap or junctions. So hand pump, single user open well, blah blah blah. Indicators, average water use for drinking, cooking and personal hygiene. So you can take your time to go through this slide. So let's go to the other part of the network. Join the network, add tank. So you can also click on, actually I've not modeled any tank in this work. So let me go back to Epanet and show you that. So you click, this is symbol for tank, so add the tank. For example, this tank here now. Let me click on, I've already modeled it. So let me just click on it. Click on the properties for it. This pen and paper button. Click on it to show the property of the tank. So tank 101 has elevation of 43.7, initial level of 5, maximum level of 10, diameter of 15, as seen inside that brief that I sent, that PDF. And because I have not run the analysis, I have not run the model, that's why you will see that the net inflow is not displayed, not applicable, elevation not applicable, pressure not. That's why you are not seeing the results. Once I run the analysis, you will see the results. But let's leave that for now. So join the network, set parameters for the reservoir. So also model the reservoir also. Initial water level in the reservoir is 1 meter. Then adding the pump. So you should also add the pump. Now, before you can add pump, let me show you around. For example, this is the pump, of course. But before you add pump, you have to add the pump curve. Because when you are modeling the pump, it will ask you for pump curve. So the best thing to do is to first of all come to object browser here. This object browser. Come to this object browser. Then click on data. Then under data, you see another button to press. So click on this down button. Then select curves. Click on curves. It's because I've already modeled a curve there. But let us know that I want to model another curve. So click on this add button beneath it, beside this cross symbol. So click on add button. So once you click on add button, to bring you to a blank space where you input the pump data. But for now, I want to just use what was there before. So this new one. Yes. So come to this former one, open it, open the property. Then you see you can give it a description, edge flow curve for the 3 pumps. Pump, then the edge equation. Actually, you are not the one to determine this equation. Once you give it this data, the software itself will generate the equation applicable to it. So this is the pump data that we were given inside the brief. So this is the curve. The pump, and this Epanet will draw the pump curve by itself. And then once you have this pump curve and all the details, and actually this flow and edge table, you see that it looks like an Excel table kind of. So which implies that actually you can load the data from Excel. You can load it from Excel. And to make a lot of things easier in this Epanet, if you later get good with it, there's a way you can, instead of inputting each node and pipe one by one, you can model everything from Excel and then import it. It will make the work faster. Or you can model it in Excel, convert it to text file, arrange it properly, insert it back, and it will make the work faster. But you need to get good with it before you can do that. So these pump details, all the 0.0 and 101.4 up to the 3rd line, you can bring this one from Excel by loading it. You can load it from Excel. You see .crv file. So you can load it from Excel. You can have the data before, stored somewhere before. You can just load it instead of entering it one by one. So let's close that. That is that one. And now the curve ID is very, very important. So our curve ID here is 1. So when you are now modeling for pump, you know that this curve is for pump. So when you are modeling for each of the pumps, you have to be putting under the curve ID, you have to put 1, 1, 1. So if you name your curve as 20, under your curve ID for the pump, you have to put 20, 20, 20. So it's very important. So after you have modeled the curve, you can now come and select the curve and the pump here. Then add it to the model. Like here, you can select the pump, click on pump, then come here, drop it, drag and drop. Let me select. View. Show. View. Backdrop. Hide. Select. So now this is the pump that has modeled before. And now you see, I was trying to drag the pump so that the way I was dragging nodes before, for node now is not dependent. It's not object dependent. It can be dragged and dropped on its own. But for pumps relies on 2 major points before you can model a pump in Epanet. So initially when I was trying to drag a pump and drop it, it was not working. Why? Because I've forgotten that pump is object dependent. You have to have 2 nodes or 2 connecting points before you can put a pump in between them. For example, now I can do that now. So you can only have pump in between 2 objects, like between 2 junctions, or between 2 nodes, or between a node and a reservoir. And even between pump also, you can have that also. So let me delete these new objects. They are not relevant to our model. Yes. So I've deleted them. So that's how to model the pump. And then, I did not show. Okay, let me come back to one of the pump here. Then properties. Now, under the properties, so you see, for the first, this 201 pump, the pump ID is 201. Now, come to pump curve. The value is 1. Why? Because your pump curve here is given a value of let's come to cups, 1. So your pump cup here also should be 1. Very important. So after you model that, you can close that and then come back to, and then the efficiency of our pump, from the brief, they told us that our efficiency of our pump should be 75%. That is 0.75 rather. So don't forget that 0.075. So don't forget that. And we have up to 3 pumps. So give all of them 0.75 as their efficiencies. 0.75. So that is that about that. So let's go back to the slide. Okay, so we'll soon be rounding up. Just remain few slides to complete. Now join the network. So adding the pumps. After adding the pumps, so add pumps between 2 nodes, between a node and a junction. Bear that in mind. So you can add the properties of the pump as seen here. Then create the pump curve as I said initially, and then add the identity of that pump curve to each of the pumps that you have modeled before. So the same thing is being explained here. Then adding the pipes. So you add pipe between nodes, between node and tank, between node and reservoir. Then join the network, adding the pipes. So the pipe property also, you have to include the length as seen inside that brief that I sent. Length, diameter, roughness, and the likes. So you put all these properties. Then the status, check it with the one that is going to be opened or closed. Very important. So adding the rest of the links. So add the rest of the links so that the network will be complete. Then be careful and make sure that you add the specific property of each of the pipes. If it is a PVC pipe, know the kind of roughness coefficient to use for it. If it is cast iron pipe, know the kind of roughness coefficient to use for it also. So after adding the pipe parameters and the length, diameter, and everything, so you can just go to the next stage, which is running the analysis. Now, this is our time. We want to run a time analysis actually. We want to do time analysis. So, because it's a community network, so we want to actually examine each of the nodes and see if the water will be adequate at a particular point in time. And we are given the data for each of the location already. Here, they said the residential demand pattern is given as this. The commercial demand pattern is given as this. So let's go to Epanet and model this table 3 and table 4. So come to this project object browser, come to data, then come to patterns. But first, go to options. Before you go to patterns, go to options. After options, scroll down to times. Select times. Now, total duration, we want to do only 24-hour analysis. So under this duration, put 24 hours. So after that, after including that, you can leave the other ones in the default mode. You can close it. So after inputting the time as 24 hours, if you want to do 72 hours, then you have to put 72 hours here. But we want to do 24 hours, so 24 is okay for the brief that we were given. So after that, you can close it. Then come to data. Now, come to under this data, click on this down button, then go to patterns. Then insert the patterns for now. If you are starting afresh, of course you will not have this residential and commercial. It will be blank. So for example, if it is blank, you just click on this add button. This add button, click on it, then give it a name. Residential pattern ID, give it a name. Description, for example now, res, that's the ID. Give it a description. Residential demand pattern. But for now, we will follow what has been there before. So after doing that, let's say res, then give it a description, blah blah blah. Then give under the multiplier, give it a particular value as given in the brief. Let me check the brief. For example, residential now at 1 o'clock 0.68, at 2 o'clock 0.55, 0.51. So come here 0.68, 0.51. As I'm inputting the data, it will be plotting the graph for you automatically. Imagine if I put 3 here now, it will quickly plot the graph. So but all these ones are not relevant because we have it there already. But this is how it is. This is how it is. Then when you are done plotting, when you are done inputting all the values, just click on save and continue. So for now, cancel. You don't need it. Delete it. Yes. So come to residential demand pattern and look at how it is. So you have already input all the demand pattern for it, 0.68, 0.51 up to the 24th hour. So let's go to look at 24 hour 0.68, at 20, that is 8 p.m. in the evening, 1.36. And this is the plot. Look at the way the plot is rising and falling. So that's the demand pattern. So the time that we have the highest demand is at 18 and 19 o'clock. That is 6 to 7 p.m. That's when the demand is very high. So for commercial, let's check that on commercial. Close this window. Commercial. Look at it. No demand from 0 to 6 a.m. No demand from 6 p.m. to 12 a.m. But there's demand from 6 a.m. to 6 p.m. Actually, that's reasonable because for a particular marketplace, I think this is actually reasonable. So once you've input all the demand patterns, then you can now run a time-based analysis. So let me go back to the slide. So in the object browser, so as I've shown you, as shown also times, then change it to 24 hours. Then in the object browser, click on pattern, then add the button, then input the data, pattern data for everything. Then under the hydraulics, so you check the material that you are given. For example, this brief, let me go back to the brief. In what units were we given the flows and the likes? Baseline demand residential, liter per seconds. Let's go and check for pipes. So I can see the data given in liter per seconds. So that means when you want to do your under hydraulics, you have to change everything to change it to liter per seconds, not gram per minute. So under hydraulics, let me go back to the Epanet software, hydraulics patterns. So this is data. Come to project browser, data, then click on the down button, click on options. Under options, click on hydraulics, double click it, and then under flow units, click on liter per seconds. So it's already actually in liter per seconds before. But if you are giving gallon per minute or any other options, you can click on them here. So for now, we leave it as it is. Nobody should call. So we are almost done with the modeling. We are almost done with the modeling. So come to inserting the pattern. So after inserting the pattern, so come to running the system. So single analysis, and this is actually time-based analysis. Running the system. So once you input all the necessary things, so you can just come to run the analysis. Click on this fire button, or as I said initially, go to project, run analysis. Either of the two options. So click on fire button. Run was unsuccessful. See status reports. Undefined curve 0.75 in energy section. Efficiency 0.75. Undefined curve 0.75 in energy section. Blah blah blah. So that means the pump property is not accurate. So let's go and correct that. Efficiency of pump curve. So let us know that it is actually 100%, and let's run the analysis. Run was successful. So you see, the run was successful. So I need to review the network to know the reason why it is not accepting 75% efficiency. So the analysis have actually run, and you can go to a particular link, a specific link, to examine it, to examine what is happening there, at a particular junction or in a link in the network. And I think that is that about that. Then you can check the summary reports. Before we call it a day, let's check the summary reports status. So it has run successfully. So this is the background information about the analysis. Then go to report again, click on full report. If you click on full report, it will give you a text kind of format. Click full report, then generate the full report. Actually, there's no time for that. Then table. So let's look at a particular graph. So for link for pipe 37, let's look at what is happening at pipe 37. Look at the graph there. Okay. I have to select a parameter that I want to examine. I want to examine the flow in that pipe 37. Okay. Now look at it. Look at the way the water is flowing there. At a particular point, between 15 and 20 o'clock, that's when the water flow rate in it is very high. So now let's look at the last part of the. Let's look at a table, just a single table. Let's do time series for link. So this is the table, and this table you can extract it to Excel and the likes for further analysis. So I think that's that about that. Let me go back to the slide. So for pipe 4, so this is node for node 1, this is the graph for it. So the materials used in this presentation was gotten from Epanet's Environmental Protection Agency website, and also part of the slide was gotten from a presentation by sheltercluster.org. Also, the textbook used was Featherstone and Aluri, and some of the materials used here are gotten from Professor Oladipo's class notes. Thank you very much for listening to class. Now, the paper that I put at the end of the slide is actually a greeting here in my PPA, where I'm doing my NYC and my youth service. And it means end of discussion. The paper means end of discussion. So thank you for listening. Thank you for listening. Any question? Okay, so if there's no question, hello team. OJB, how far? Hello JB, how far? Ma? What you say? Hello OJB, I'm with you. Okay. Okay. Yes, sir. Go back to it. Yes, through YouTube. Yes, yes, yes. Okay, sir. Okay, sir. All right. Thank you very much, sir. Yes, sir. Thank you, sir.